Hey everyone, Kianski here, back again from a short break. Today I'm going to be showcasing a little demonstration I made that I actually posted up on my Twitter page, and it got a lot of attention that I wasn't really expecting, and a lot of people were asking me, how do you make this? So I decided to make this video just to show you all the steps that kind of go into making this. A lot of people were asking me, is this AI, or is this some sort of magic? But really, it's just pretty simple yet practical math, specifically in C-framing for the arms, and then in trigonometry for deciding where to put the ball. So really, just some kinematics and some trigonometry, and a little bit of physics as well. And that's what kind of goes into doing something like this. So in this video, I'm going to be splitting it up into some parts just to break it down. In the first part, I'm going to be showing you how to use inverse kinematics to move an arm to a desired position so that I can grab it, and then also how to interpolate it between two positions so that I can move from one position to the other in a smooth manner. Okay, smooth and natural. And then in the second part, we're going to be how to find the angle of the ball relative to an arm, so it knows where the ball is relative to the arm, and then how to change that angle and move the ball in a way where it goes in a circle around the arm so it can throw it. And then lastly, how to actually move the ball from one arm to the other, and also figure out where it's going to land so we know where to put the other arm so it can catch it. Okay, so it's going to be a lot simpler than you might think. I'm just going to explain it, break it down into those segments, and then at the end of the video, I'm going to go over the code and just kind of show you the actual finished product. And all the code and all that will all be in the description. So you don't have to write anything out. You just have to watch and learn, and hopefully you learn something new. So let's get right into it. All right, so for this first part, we're going to go ahead and actually make the arm and do most of its functionality, where it moves from any desired origin position to any desired target position. And if I move this blue part, you can see that the arm actually chases to its best ability to wherever I put this blue part. So we're just going to make this part of it. And what we do for this is called inverse kinematics, which is just positioning each of these parts in such a way so that it follows a position. That's really what it is. So we're going to go ahead and do that. I have a script here. I'm going to delete all of the all of the inverse kinematic stuff, and just leave the part that makes the arm, which is this part right here. So if I go ahead and run this, I'm just going to have an arm of 5 segments. Each of these segments I've made 5 studs long, right here, 5 studs long, and positioned them 5 studs apart, with an offset of 2.5, so that it starts with the tail, goes to the head, like so. And I've put them in this segments table, and I just wrap them with a table. That way I can add a meta table. Meta table just says, if I index with head, give me the C frame that's 2.5 studs forward. If I ask for tail, give me the C frame that's 2.5, or actually give me the position rather, that's 2.5 studs back. If I index with anything else, just index the part. And if I write to the part, if I write to the segment, then just write to the part with that key and value. Okay, so so first things first, the first step in getting the arm from A to B is actually moving the last segment first. So this is inverse kinematics, so we start with the last segment. Forward kinematics would be the opposite, where you start with the first one. I just chose to do inverse. I think that's a little suited the project a little bit better. So the first step is to actually move, or actually rotate the last segment. So I'll do segments. Since I have 5 segments, I know the last one is just going to be segments 5. And I want to rotate it using C-frame.lookat. and I want to position it at where it was at the tail. So segments 5 dot tail, and I want to look at the target position. Okay, so if I go ahead and run that, you'll see that the last segment has already been rotated towards the target position. Now all I have to do is move it. How far do I have to move it? Well, it's just going to be forward, and the amount of studs is just going to be the distance from the head of this segment to the target position. So this distance, move it forward. Okay, so that should be pretty simple. Segments 5 dot C frame equals, now the distance should be, it doesn't really matter which order I put this in since I'm just getting the distance, but it would be from the head, so segments 5 dot head to the target position, so target dot position, and then to get the distance of that, just call magnitude on that. And then I want to say C frame, or actually I want to transform this. So I'm not setting the C frame, I'm now transforming it. So times equals C frame dot new 0 0, and then negative this amount, because forward is the negative Z axis. So I'm going that position in the negative Z axis, and as you can see, the head is now exactly right on the target. Okay. The next step, okay, is, if I run this again, is to do the same thing with the fourth segment, but instead of moving it to the target, moving it to the tail of the one in front of it, which would be segment 5. So move segment 4 to segment 5, and then move segment 3 to segment 4, and so on. So I already have some code to move segment 5, but I'm going to go ahead and turn it into a method and parameterize it so that I can use it for all the segments. So I'm going to do local function move segment that takes in a segment and a target position, and just go ahead and rewrite this function so that it can be used for any segment. So just rename those two to just segment, this one to just segment.tail, this one to just target position, and this one to just target position, and this one to just segment. And I think that is it. Yeah, that looks like it. Yeah, that looks good. So if I go ahead and move segments 5 to the target position, it should work just fine. Okay, cool. So it works the same way, just now I'm calling a function, move segments 4, and my position that I want to move it towards is the tail of segments 5. So segments 5.tail. Okay, and as you can see, segments 4 has now been moved to the tail of 5. Just going to repeat this process 3 more times. So 4 goes to 5, 3 goes to 4, 2 goes to 3, and 1 goes to 2. And it looks pretty good. So one thing that has to happen afterwards, though, is if I go ahead and move this part to where it can't reach it, what will actually end up happening is the arm gets completely dislocated from the origin position, which is, for my project, I obviously don't want that. So I want to keep the origin and the tail of the first segment at the same position. So what I need to do is actually run this again. Once again, we need to find the difference in positions. I need to find the offset. Okay. I need to find the position from the tail of the first segment to the origin position. So that position right there. Okay. So we'll go ahead and find that. That should just be, I'll call this the offset. And we'll say target position, or I'm sorry, origin dot position, from the origin position to the whatchamacallit, segment 1. Okay, dot tail. And this order actually matters because I want the offset from the origin position to the tail. So I do tail minus origin position. Okay, and then I'm just going to go ahead and subtract this offset from all the segments. So segments. Actually, I can do this in a loop very easily. So for I equals 1, 5 do. Segment dot, segments I dot position minus equals offset. Okay, so I'll go ahead and run that, and as you can see, the arm has been moved back to the origin. Okay, and I can repeat this whole process whenever I want to move the arm a number of times. And that gives it more iterations, so it can, if the part in question, now the arm is actually more straightened out because it's been given more iterations to follow the target. Okay, and then I want to wrap this whole thing in a function so I can call it whenever I want to. So move arm to target. Okay, and then we'll just call that function every wait. So while wait do move arm to target. And so if I go ahead and move this blue part, we get some arm movement, which is pretty cool. Last thing I want to showcase is how to linearly interpolate between two target positions, because I actually do this a lot in my final project, and I think that it's pretty important. So we'll go ahead and just show it real quick. I'm going to have two targets. I'm going to rename this second target to target 2. Add that to my variables up at the top. So target 2 equals workspace.target2. To interpolate this, I need some sort of time variable. I also need a lerp function. Lerping takes in a start position, an end position, and a time, or some sort of alpha, right? To choose how far to go from one to the other. And I just want to return A, that's my starting position, plus the difference from A to B times that alpha or that time value or whatever. Okay, and so for my time variable, I'm just going to start at 0. Instead of putting wait here, just call this while true do, and then say t plus equals wait. Okay, so that I am keeping track of the time. And then if t is greater than, so I want to do 5 seconds, or maybe no, we'll do 3 seconds. So if t is greater than 3, t equals 0. So just go back to 0 after it hits 3. And then actually I want to re-parameterize this function so that I can take in any target position, not just the static target. So I'm going to rename this to target position. And then to figure out what our target position is, I'm going to interpolate from target position 1, target position 2, and use the time variable divided by 3 to figure out where it needs to be. So I'll do lerp target position 2, and t divided by 3. Okay, so however much time we're in, divide that by 3. So that figures out how many seconds we are in the interpolation, and then move that amount from target 1 to target 2. And then, of course, pass in the target position. Okay, so if I go ahead and run, as you can see, it lerps from one target to the other, and it just repeats this process because I have it in a loop. Of course, if you want to ease this, I would go ahead and wrap this in some parentheses, and then, cube it or whatever, raise it to some power. And now it starts off slow and gets faster as it gets closer, okay? And if I want to do the opposite, I'm gonna need it's gonna be easier if I write a flip function. So this is really easy, just 1 minus x, right? And then what I'll do is I'll, before I raise the third power, I'll flip it. So flip t divided by 3, then raise that to the third power, and then of course flip it again. And if I run that, it'll start off fast and then get slower. And I believe that's actually what I use for when I move the arm to where the ball is going to be. I have it start off fast and then get slower. So this is actually what I do. Although I raise it to a higher power, I think I raise it to like 7. So this goes really fast and then slows way down. So yeah, so very fast and then eases in as it gets really close. Okay, so that's it for inverse kinematics and lerping between targets. We're just going to go ahead and move on to the next thing. Okay, so for this next part, we're going to be showing you how to take the angle of a target and rotate it around an origin. And this is going to be important because when the arm is going to be throwing the ball, it's going to go in a circle around the origin of the arm along a plane. So what that looks like is if I run this, it just moves the target around here, and we're going to be interpolating wherever the arm currently is to where this target is, so it can follow it and it can make the throwing motion. Okay, but the important thing is that the target, wherever it is, that's where it has to start rotating from. So if it's over here, it's going to start rotating from here. So if I run it, it kind of starts from the closest point on the plane right there. However, if I move it to somewhere completely different, like up here, I run that, starts from up there, and the closest point on the plane that's in the radius of the circle, that's where it's going to start. Okay, so I'm just going to go ahead and delete everything except for my 2 variables that just say what the origin and the target parts are. Okay, and so first things first, we need to figure out what is the current angle from this and some other arbitrary vector. Okay, so for example, if I wanted to find the angle from here, from this vector and straight up, then I would take the vector from there and the vector for up, and I would do the dot product, and the dot product is the same thing as the inverse cosine, or I'm sorry, the dot product is equal to, for 2 unit vectors, the same as the cosine of the angle. So you just take the inverse cosine of that and you'll get the angle. That's just a general rule of thumb for finding angles in any math application. So let's say I wanted to find that. So I want to do up direction equals vector3.new 0, 1, 0. And then the direction from the origin to the part is going to be target direction equals, so to the target direction, so target position, sorry, from the origin position. And then just get the unit vector of that, because you just want it as a unit vector, and of course this is a unit vector because it's just 1 unit in magnitude. Okay, so I'm going to get the dot product of those 2, and I'm going to get the inverse cosine of the dot product. So the inverse cosine of the dot product of 2 unit vectors is always the angle between those 2 vectors. It's non-directional, but we'll get to that in a second. So local angle equals, let's see, dot product, yeah, math inverse cosine, target direction. It doesn't matter which one you call dot product on, because dot product is, it doesn't matter which order you do the dot product in, it is the same result every time. And of course, to make this more readable, I'm going to change it to degrees, and then I'm going to print that angle out. Okay, so this is 41, which makes sense because if you kind of look at how this is positioned and which direction is up, this is about 41 degrees, which looks about right. And if I were to go ahead and move this part to somewhere like this, it would be about 90, and which it is 94. That is a 94 degree angle right there. Okay. All right. Now for my arm throwing, I actually wanted to find the angle from not the up direction, but from the forward direction. So I'll go ahead and get that. Local forward direction equals vector 3. And of course, forward is -z, so I do -1 on the z-axis. And then my angle is going to be target direction dotted with the forward direction. Okay? And if I go ahead and run this, you'll see that it's very close to 180. Also, I don't care about any if the target has any x difference. I want to eliminate that completely. I want my target direction to just be on the z and y plane. Okay, so I'm going to eliminate the x component from my target direction, and to do that, I'm just going to go ahead and take target direction, this is the target direction, or the target difference, I should say, times vector 3, 0, 1, 1, and that'll multiply all the x's by 0 and just keep the y and the z the same, and then take this whole thing and get the unit vector of that. Okay, so it's still a unit vector, it's just I've eliminated the x component, and we're just on the YZ plane. And that way, if I get an angle for this, run it, this is 141, so to draw that, that'd be to here, 141 degrees. And if I just move it the x-axis, it should still be 141 degrees. Yeah, so it's still the same regardless of where it is on the x-axis, because I just want to know where it is on the y, the up and down and the forward, that plane. Okay. So moving on, now that we have the angle, the only problem with our angle is that it's not directional. Okay, so I mentioned that earlier. What that means is that if I have it here, and let's say this is again 141 degrees. Okay, if I get 141 in my output as my angle, there's no way to tell if that 141 degrees is this way or if that 141 degrees was this way down. Okay, so let's say the part was right there. There's no way to tell. The angle doesn't have a direction. It doesn't really care. Dot product, the inverse cosine of the dot product only goes from 0 to 180 degrees. Okay, so if it's the other way, there's no way to tell. So the way to tell, okay, is to have another dot product in a 90 degree direction. Okay, so what does that look like? If I go ahead and use my up direction again and say if target direction dot up direction is less than 0, so that means we're in the opposite direction of the up direction. So if we're less than 0, that means we're in opposite directions of the up direction. If it's greater than 0, that means we're in similar directions as the up direction. So I'll go ahead and draw that in a second. But if it is less than 0, I want to take the angle and I want to set it to 360 minus that angle. So that will give me the, I believe it's called the complementary angle, I'm not entirely sure, but gives me the direction of the other way. Okay, so if I go ahead and run this, this is still 141. Okay, cool. But if I move it down to below, so now the target direction and the up direction are pointing in different directions. This will give me a dot product of less than 0. If it was up here, then that would be greater than 0. Okay, so if I go ahead and run this, it should give me a value of greater than 180. It gives me 212. Okay, so 212, instead of giving me now the angle from here to here, okay, instead it gives me the angle from here to here. So now I have a completely directional from 0 to 360 degree, and that's exactly what I want. Okay, so I have a directional angle. So going back, now that I have the angle, now it's time to start positioning the target to right where I want it to be, and then in a loop increment the angle and then move it to the next angle along the circle. So what does that look like? I'm just going to do a while wait my x. To convert an angle to a position on an x and y axis, you use cosine and sine. So local x equals math.cosine. Of course, our angle was converted to degrees. I need to change it back into radians and put the angle in there. Local y equals math.sine, math.radians angle. And then my target position will be set to the origin dot position plus a vector 3. Now my y is on the y-axis. It's already aligned, so I can just put y in the y. My x is actually on my negative z, so I need to put negative x in the z component. It's because x is supposed to be forward, negative z is forward, so I put a negative x in there. And then the radius of the circle is just going to be, we'll just say it's 25, and that kind of makes sense because if there's 5 arm segments and they're all 5 studs long, the radius of the circle is going to be 25. Next, I'm going to increment the angle by some amount, so I'm just going to do 3, and then keep the angle within 0 and 360 by using the modulo operator. So angle equals angle modulo 360. And if I go ahead and do that, you can see we have what we started with. So wherever this part is, it's going to start from that angle and then just rotate, spin around the circle as such. So that's going to be pretty important for the arm throwing mechanic. So yeah. Okay, so for this last bit before we actually look at the project code, is we're looking at how to move a ball in a simulated way with simulated gravity, because in my project the ball doesn't actually use physics, it's anchored, so its physics is turned off, and we just move the position of the ball each frame. And the reason I do that is so that I can easily find the positions of where I want the ball to be in the future, and then just move the ball along that path. And since I know where the ball is going to be in the future, I can just move the arm to that position and have the ball and the arm touch at the same time at the same place, and it makes it really easy. Okay, so just going to go ahead and show you how to just do something like this and how to know all the positions of where the ball is going to be ahead of time. So it looks like the ball's moving, but you're really just moving it with kind of like simulated gravity. Okay, so I'm gonna go ahead and just delete all of this. I just have to wait beforehand so that it takes a second before it runs, so that way I can actually have time to see it. My ball is just the part workspace.ball, and I just need some values for certain things like gravity. So the acceleration of gravity, if you actually want it to be the same as how it is normally, it's 0, negative 196 in the y direction, and then 0. So it just pulls things down at an acceleration of 196 studs. I want my starting velocity to be just some numbers. It doesn't really matter, but some numbers that look nice, I think, are 100, 100, and negative 100. This is just a little bit on the x-axis, move it up on the y, and move it out forward on the z, okay? Next, I need a table for my positions, because we're going to be storing every position along the path in this table. And then I need an amount of time that I want to wait in between each position, and that's just going to be delta time, and I'm just going to do task.wait. It's very simple. We just get delta time ahead of time, and we just use the same delta time throughout the rest of it. I'm not really concerned about frame rate, so I'm not concerned about getting a new delta time every frame. I can just get one and then just use that over and over, okay? And then my current position is the ball dot position, and we're going to be updating current position and velo as we move along. So I'm going to do a loop, okay? So while true do, and then I'm immediately insert into my positions whatever the current position is. And then I'm going to have some sort of break for this loop so that I can break out of it when it's finished. So just for this example, I'll say if current position dot y is less than ball dot position dot y, and I'm not moving the ball at all, so the ball position isn't moving, and I'm just seeing is the current position less than the original y, and if so, then break out of this loop. I then want to update my velocity. Whenever velocity changes with acceleration, the only acceleration I have on the ball is gravity, and the amount that I want to add to it is just gravity times the change in time. So the acceleration times change in time is a change in velocity, okay? And then the same thing for the position, current position. The change in current position is going to be the change in not the change in velocity, but the current velocity times the change of time. So change of time times velocity equals change in position. We just add that, okay? So now this will loop through until it gets to this breakpoint, and then I'll have a table of positions that I can iterate over, okay? So if I go ahead and just visualize this, so I'm going to iterate over all the positions. So for position and indice pairs positions, I'll just make a part. This is my part. I just anchored it, sized it, positioned it, and paired it to the workspace. And you can see the path of the ball before it even moves. So now all I have to do to move it is ball.position equals position, and then add some sort of weight that's similar to my delta time, and it's just going to work. And there you go. That's how you move the ball and simulate it as if it were moving with real gravity. Okay, so let's go ahead and actually look at the final project and kind of see how all of those topics kind of get put together into this code and how it all works. So I'm going to stop this now and open up the script. And it isn't the cleanest code ever. I just kind of wrote it up really fast. Kind of took me only about 20-30 so minutes, and maybe I spent another 30 minutes polishing it, tweaking it to do exactly what I wanted it to do, because I knew I was going to record it for a video and put it online. So here we see I have three parts: the arm, the other arm, and the ball. And I go ahead and initialize the segments for both A and B, and I have segments A table and segments B table, and it's just going to be segments 1 through 5 for each arm. And I have a lerp function. We saw that earlier. I actually edited mine a little bit to specifically behave differently for a vector. I want the x1 to ease harder than the y and the z. This is not something that you really need to do, but I want it, as you can see, I have the a plus b minus a times t for each of them, but the x-axis is just brings the t value to the third power for the x, just so it eases harder on the x, whereas the y and the z is just normal. That was just a minor, again, that was one of the minor tweaks that I made to it, not a real big deal there. Here's my move function. It's a little bit different than the way I had done it in where I showed you how to move a segment. Again, that's because this isn't very clean code. This is kind of the way I coded it the first time. So naturally, when I go to do it for the tutorial, I do it much cleaner in the tutorial, but that's just how I did it. It's the same thing, just rotates it and then moves the position to wherever the target is. And then I have a move segments A and a move segments B. Of course, this could be the same function, just for a different segments table. But again, I just made it into two different functions. No big deal. It's whatever. But that's what that function is. And then this is actually where the code really starts. So this is where the loop starts. And the first thing I do is I put the ball in the arm of arm A. So I have arm A and arm B. So ball.cFrame just goes into the head of A. So segments A, C-frame, and then 2.5 cents forward. I didn't put up any meta table for the segments or anything like that. So every time I want to get the head or the tail, I have to multiply by C-frame that new by either negative or positive 2.5. Again, not super clean, but that's just kind of how I coded it the first time. Then we go into the arm A throw code. So this is where the arm A throws the ball. So I get the direction to the ball, and then up and forward direction, just like I did previously. Get the dot for the ball in the up, the ball for the dot in the forward. I do it a little bit differently, and it's not as it's a little bit tiny bit different because I do the ball in the up instead of the ball in the forward. So up and forward are kind of flipped here, but it's the same concept. This is the exact same concept. The only difference is that when I go to here, I have to add math.pi over 2 because I was 90 degrees off and I wasn't sure why. Well, it's because I put up instead of forward, and so I had to add 90 degrees here in radians to make up for that. But again, same concept. It all worked in the end. And then when I figure out the angle, I say, okay, angle left is equal to the current angle plus 360 degrees. Now we're gonna rotate that many angles, like that many degrees, starting from, and the target will start at the ball that position, and we'll find the we're gonna go in a circle and make our new target to wherever that y and x is, and make that our target. Every run service.heartbeat wait and lerp there, and then move the segments to that lerped target, and move the ball as well to that target. And then if the angle hits some sort of threshold, then break out of this loop. If not, then just set last position to target and adjust the angle. And I just did it by 8 every wait. And of course, if I increase it, it would increase the speed of the throw. Okay, and then The whole point of getting last position and new position is to figure out how much change there was at the very last, like right when the arm is done throwing. What was the change from where it currently is in the last position it was at, and then that's the change in position, and then velocity will be change in position over change in time. Change in time comes from run service to heartbeat weight. Okay, so now I have change in position over change in time, so I have velocity, and then I just add a little bit of randomness to it on the x-axis, so it goes a little bit to the left, a little bit to the right sometimes, and that helps showcase the arm's ability to go left and right as the ball has a little bit of randomness to on the x-axis. So it's not just catching it straight up and down, it's catching it up, down, left, and right. Okay. Then we need to find, it's now being released from the A arm, so now find where it's going to hit the B arm. Okay, so find where it's going to hit B. So we have our current position, so this is where we're doing the ball gravity stuff. We have the positions just like we did last time or earlier, let's see, I add the velocity to my current position, then I do some checks. This is where I check to see if we're inside the arm zone where it can catch the ball, or if it's gone past it, because it's actually possible for it to not ever hit the arm zone of where it's trying to throw it to. And so I cheat a little bit and just say, okay, well, if it's going past it, if the position is now getting greater, then we have to just say, okay, that was the closest point to where it's getting to the second arm, so that's the closest point. So you'll see that sometimes where it'll throw the ball and it'll be so off. Here, I can actually make it where it's definitely going to be off. I'll make this like 400 or something, or like we'll make it probably 80, I think would be good. So yeah, so that right there is what you just saw. So if the ball is for sure not going to hit the zone, but now it's getting to the point where it's like now it's getting farther away, well, we'll just pretend like that's the closest point to the position of the ball, or I'm sorry, to the position of the arm. So that's the closest point, so we're just going to catch it there and just move it to the arm later. So that's my little cheat right there. Not a big deal because it's just a showcase. You know, it's not supposed to be realistic or anything. Yeah, moving on. So we got all the positions just like I did earlier. Again, not as clean, but it gets the job done. And I add gravity right here, by the way. So I'm changing velocity here, changing position here, and inserting my new position here. And this is my brake. Okay. And this is also a brake as well. So it's a little bit not as clean, but that's why you refactor code. Okay, and then now I know where the position the position that's going to be closest to the arm, so I know where to move the arm, and I know where to move the ball. Every step I'm going to get the this is the T value. I called it alpha here, but it's the same thing. Lerp the move segments B, and also move the ball position to its appropriate position, each heartbeat weight. Once it's done doing that, the ball has now moved all the way to the closest point that it'll ever be to the arm. So just move the ball right into the arm of B. So that's the segments B5 head. So move it 2.5 forward, and that's it. That's actually it, because that's the halfway point of this whole while loop. Okay, right here, it's the exact same code, but for arm B. So it does. So this is throwing from arm A to arm B all the way down to here. Once it gets to here, it just does the same thing with slightly different values. So I could have parameterized it and made this whole loop much shorter, but I just kept it like this. And then arm B throws to arm A in pretty much the exact same way with the pretty much exact same code.
and it can, yeah, that's the whole loop. And then once that finishes, it just repeats, rinses and repeats. It does the same thing over and over and again. Okay. Yeah, so that's how I did that, and hopefully I made this seem a lot simpler than it may have seemed when you just look at it, because it really is just moving the arm to the ball using some kinematics, finding the angle of the ball, and then moving the ball to the other spot. I mean, that's really all it is. So yeah, hopefully that helps. If you have any questions, just leave me a comment, and then I'll be able to help you, hopefully. So yeah, I know I haven't uploaded in a while, but I really plan to upload some more stuff. So just stay tuned for that, and yeah, see you guys hopefully in the next video or wherever you see me. So yeah, peace out.